So question 2 introduces a new idea, and it's called using homogeneous. We're using homogeneous coordinates. So instead of an x, y ordered pair, we're going to use an ordered triple x, y, 1, or we could use x sub 1, x sub 2, 1. And all this does is, if you imagine the x and y plane being in the surface of the paper, all that does is take any xy pair, let's say it's the pair 2, 3, it takes that point and we imagine it to be the z-axis coming out of the paper, and it would raise that point 1 unit in the z direction, which, if you're looking at a computer screen, that won't change position, whether that point is here or here or here or here. As long as it's in line perpendicular to the plane, it will look like it's the same point. So basically, a homogeneous coordinates adds an extra, it's a parameter that allows you to do some things, and we've already talked about rotations, so we're going to introduce this parameter so we can do some shifting of figures. So, because we can't do any translations, all we've been doing is rotating and stretching and shrinking, and that's all you can do when you have just the regular rectangular coordinates. But with homogeneous coordinates, you'll see we're going to be able to slide these figures. So this provides us an extra parameter that we can add something to these, one or the other of those variables, of those coordinates. So if you have a partition 3 by 3 matrix and homogeneous coordinates for your figure, to perform the same transformation, what would B and A have to be? So instead of just x sub 1, x sub 2 as your two values, we have x sub 1, x sub 2, and 1, which means this is a 3 by 1 matrix, and so B is going to have 3 columns. And if this has 3 columns, right, in order to multiply by the 3 rows, 1, 2, 3 rows, then we are going to want this to be a 3 by 1 matrix. We're going to want to keep this homogeneous, so this will have to be a 3 by 3, which means this will have to have 3 columns, and to keep it in homogeneous coordinates, to have our final product be a 3 by 1 vector, we need this to be a 3 by 3. So our B matrix and our A matrix, A was 0.5, 0, and 0, 2. B was 0, 1, 1, 0. So if we partition this, all we need to do to make a partition matrix is make these 0, 0, 0, 0, and 1 on the diagonal. And so this is a special partitioning that will give us the same thing we got before. If you remember, by matrix A times B times the vector x, we got 0.5 x sub 2 and 2 x sub 1. So here we're going to want to have, if we multiply this 0, 1, 0 by x sub 1, x sub 2, 1, we'll get 0 plus x sub 2 plus 0, which is just x sub 2. And the next row, 1, 0, 0, gives us x sub 1 plus 0 plus 0, which is x sub 1. And then this last row gives us 0, 0, and 1. So notice it does the same thing. Remember, B just switched x sub 1 and x sub 2 before, and it does the same thing here. Z stays the same. And now when we have 0.5, 0, 0, and 0, 2, 0, and 0, 0, 1, watch what happens when we multiply that. We get 0.5 times x sub 2 plus 0, x sub 1 plus 0 times 1, which is just 0.5 x sub 2. And then 0, 2, 0 is 0 times 2x sub 1 plus 0. So that's going to be 2x sub 1. And then 0 plus 0 plus 1. So it's basically the same. This was our result basically in 2 space, and this is the same result. It's in 3 space, but that 1, if we think of the z-axis as coming straight out, it's really just raised up one unit, and it would look the same as it's projected onto the xy plane, or the x of 1, x of 2 plane. So these are your homogeneous, there's your homogeneous coordinates for A, homogeneous transformation for A, and for B you just add the 0, 0, 1, 0, 0, 1.